We have already seen that transverse waves on the string transfer energy. It is natural for us to also expect sound waves to transfer energy. Let's consider cylindrical tube with a piston and there is a gas inside undisturbed with the pressure P. And then when we start moving this piston back and forth in a simple harmonic motion with the angular frequency of omega, then a very, very small amount of gas will be compressed. I know my picture is kind of exaggerated, it's big, but it's so small that we can actually model this element as a particle that moves back and forth with the same speed as the piston is doing. Well, then we can say that the piston is doing work on this element, which we can model as a particle. And the rate at which the piston is doing work on the element at any instant of time can be written as the power equals the force dot product V x. Let's suppose it moves back and forth with the speed of Vx. I have used power as a whole word rather than P so that we do not confuse power with the P pressure. So in this expression, the force is associated with the pressure and the velocity is the derivative of the displacement function. Well, let's write that down. So the force is sum of the forces that equals sum of the forces, so equals P plus delta P A minus PA, and that will give us delta P A. And let's note that this delta P is a function of x and time. Obviously, let's put also the direction I in here, and I in here, I, and then I here. So then I can write for the power, this one, I can write equals delta P xt A I hat dot product, and then for the Vx I'm going to write the derivative of the displacement function, so d dt s xt I hat. Now if we evaluate this, we can write equals for the delta P. We have found that equals rho V omega A S max sine kx minus omega t, and then d dt S max cosine kx minus omega t. So simplify this, we'll get rho v omega a s max sine kx minus omega t and then let's take the derivative. That would be omega s max sine kx minus omega t. Okay, so if we simplify this, we will get rho v omega squared A S max squared sine squared kx minus omega t. Now, the average rate at which the energy is transported can be written as a p average, and we will take the average of this expression here. So we can note that average of this term of our sine squared kx minus omega t is actually 1/2. So if we take the average of that, then I can rewrite my expression for the average power to be 1/2 rho v omega squared A S squared max, and that will be it. So that will be average power. Now, if we want to write intensity, we know that intensity is the average power per cross-sectional area. Then I can write 1/2 rho v omega squared A S max squared divided by A, and then A's will cancel out. We will end up having 1/2 rho v omega squared S max squared. Now, how intensity varies with distance from real sound source is often quite complex. Some real sources, like loudspeakers, may transmit sound only in particular directions, and environment usually produces echoes that overlap the directions, overlapped with the direct sound waves. Now let's consider special case of a point source that emits a sound wave equally in all directions. If the air in the surrounding is perfectly uniform, the sound power radiated in all direction is the same. And so we can say these spheres, these waves are called spherical waves. And then sometimes we draw arrows to show the propagation of the wave. And these circles are known as the wavefronts. So this is called, the arrow is called ray. And the distance between two spheres is the wavelength. For these spherical waves, the intensity could be written as power average divided by area, which equals, I'm going to write power average divided by 4 pi r squared. You can see that the intensity is changing inversely, is proportional to the inverse r squared. The further you go, the distance, the intensity decreases the square of that. This inverse square dependence of R is really just a statement of energy conservation. The source emits energy at the rate p joules per second. The energy is spread over the larger and larger area as the wave moves outwards. Consequently, the energy per unit area must decrease in proportion to the surface area of the sphere. Now, talking about human hearing spans, which is an extremely wide range, varies from about 1 times 10 to the negative 12 watts per meter square to about 10 watts per meter square. So this top number is the threshold of hearing. and the bottom one is a threshold of pain. So you can hear as low as 10 to the negative 12 watts per meter square, and you can hear as high as 10 watts per meter square intensities, which can be quite painful. So now it makes more sense for us to talk in terms of loudness, because that's what we perceive in general. So if we want to make a scale of loudness, it is very convenient and logical to place the zero of our scale at the threshold of hearing. So to do so, we define a sound intensity level, and we express this in decibels. So let me write the word decibels, and it is denoted as a lowercase d and capital case B. And so we define this as we use Greek letter for the sound intensity level, which is a fancy word for the loudness. We use a Greek letter beta, and we define it as a 10 decibel times log of 10, the intensity over threshold intensity. So where I naught, which is the threshold of hearing, equals 1.0 times 10 to the negative 12 watts per meter squared. So I find it's very important for you to learn that decibel is not a unit. So sound intensity level is a unitless quantity. So the decibel is named after an inventor of the telephone, Alexander Graham Bell. So sound intensity level is actually dimensionless because it is formed from the ratio of two intensities. So decibels are just a name to remind us that we are dealing with the intensity level rather than a true intensity. And it is very important that you understand that there are different things, intensity levels and intensities. So right at the threshold of the hearing, let's say if you take the intensity equals intensity of the threshold of hearing, then our intensity level beta would be 10 decibels times log 10 I naught over I naught, which will give us 10 decibel times log 10 1, which equals 0 decibel. Therefore, we hear nothing. So 0 decibel doesn't mean no sound. It means that for most people, no sound is heard. So for example, dogs have more sensitive hearing than humans, and most dogs can easily perceive a 0 decibel sound. The sound intensity level at the pain threshold, let's see if we want to find sound intensity level at the pain threshold, we just plug in the pain threshold number in this expression by 10 watts per meter squared divided by 10 to the negative 12 watts per meter square. And so this will give us 10 decibel time log 10 to the 13. So this will give us 130 decibel. So if the sound level is 130 decibel, then you have a pain in your ear. For having a better sense of what is a decibel and in general. So let's look at the certain sounds. So we know that the threshold of the pain is 130 decibel and the intensity is 10 watts per meter square. So if we look at the military jet aircraft, that will be 140 decibel, which is 10 to the 2 watts per meter square. So that is most possibly your ear will be damaged. So busy street traffic is about 70 decibel, and that is 10 to the negative 5 watts per meter square. Ordinary conversations will be 65 decibel, and that is of 3.2 times 10 to the negative 6 watts per meter square. Now, if you take the a whisper, okay, so that would be 20 decibel, and that is a 10 to the negative 11, and then rustle of the leaves will be 10 decibel, which is 10 to the negative 11. Well, I have a whisper 10 to the negative 10 actually. The rustle of the leaves is 10 to the negative 11 watts per meter square. So although we have seen that 130 decibel is the threshold of pain, well, quieter sounds can damage your hearing as well. So a fairly short exposure to 120 decibel can cause damage to the hair cells in the ear, but lengthy exposure to sound intensity levels of over 85 decibel can produce damage as well. So be careful when you're listening to music or you are being exposed to sound. By the way, talking about the music, if you go to the rock concert has about 120 decibel of sound intensity level. Well, be careful with the sounds and stay tuned for more to come, and thank you for watching.